Okay, so let's start. Last lecture we were looking at we were discussing a general purpose digital system which users can customize for their application. And what we said was that such a general purpose system, what it would do is execute internally a series of simple instructions. So the machine is capable of executing a series of simple instructions, and the user then writes a sequence of instructions which will accomplish his or her task. So that was the idea, and we said that it makes sense to store the data and the instructions in a memory, and therefore we arrived at what we call as a microprocessor. So we looked at a very simple microprocessor which was only capable of doing some addition and subtraction. A better microprocessor to study, which incorporates within it a lot of basic principles. It's only of historical importance because it's not being used now, but it's important because it's a simple processor through which we can illustrate some of the basic ideas that are found in even modern microprocessors. All right, so with that in mind, what we'll do is we'll take a look at this 8085 microprocessor, how it is organized, what the instruction set is, and what it is capable of doing. Okay, so our discussion would be very brief. Purpose is only to illustrate some basic ideas that are there here. So I put this up last time. So it's a 40-pin IC. It can run at a clock frequency of, depending on who the manufacturer is, at these values here. These will make more sense later on in the course when we talk about how we implement gates in terms of transistors, whether we use NMOS or PMOS or we use CMOS. And you can see it's a fairly complex processor in the sense that the instruction set is very large. 246 internal instructions are there, and you can so a user can express his or her requirements in terms of these instructions that are there. All right, so let's look at the microprocessor in a little bit more detail. So the instruction sets, what we call as instruction set architecture of 8085. So the first thing about it is that it can process data most of the time in forms of 8 bits. So it can do, for example, transfer from one place to the other, an 8-bit data. It can add a 8-bit data, or it can perform a logical operation on 8-bit data here. So it's an 8-bit, that's why we call it 8-bit microprocessor. The address is 16-bit. Remember, all our, this microprocessor will be interfaced with memory. So the entire program is going to store in the memory. So 16-bit address basically tells you that you have 64 KB memory available. So that's the maximum memory that you can interface to your 8085. So 16-bit address bus. This we'll see a little later on. These are the, inside the microprocessor, these are the some of the registers that are there here. There's a register called accumulator. It has a special importance we'll see in a minute. There's a register called flag register here. And then there are registers like B, C, D, E, H, L. There's a register called stack pointer. This is a new word for us. Program counter we've already seen. Keeps track of the memory location from where the program, the instructions have to be fetched. So program counter, because note that the address bus is 16. So program counter has to keep the address. So that's why it is also 16 bits here. These are individually 8-bit registers, B and C, but it's possible to combine them and into one single register, which becomes a 16-bit register. So 8085 instructions allow you to consider B and C as one single 16-bit register. And similarly, D and E could be considered as one single D resistor. So it becomes a 16-bit resistor here. And HL again as one single resistor here. So it has those options that are there. As I said, accumulator and flag are special registers which you'll see here. All right, 16-bit BC, 16-bit DE, 16-bit HL. All right, so let's look at, so these are the registers which are there. So let's look at the 8085, the microarchitecture. We'll look at the instructions a little bit, but basically the instructions would be what? They would be moving the data around within the microprocessor from one register to the next register, moving the data between the internal registers and the memory, right? So you realize RTL is what? RTL is moving data around inside, between the memory, between the registers. So there are instructions on that. And then there are instructions on adding, subtracting, doing logical operations. And then if you're writing a series of instructions, it's not that you execute instructions in a linear order. You may at some point want to jump to some other instructions. So there are jump instructions. So instructions are basically in those categories which we'll see. So if I describe the 8085, the microarchitecture, so as I was explaining, all in order to facilitate connection between different registers and different units, instead of dedicated wires running between two units, we have a single bus which runs through the system. So here is a data bus. This is a conceptual diagram here. Data bus which runs here. We have an arithmetic logic unit which can perform arithmetic and logical operations here, ALU, we call that. There are two important registers. One important register which I mentioned is the accumulator. And there's an internal register called temp, which is not accessible to the user directly. All right, so the ALU receives inputs from here, directly from the accumulator and from this temp register. The results of the ALU are put back on the data bus. And most of the time what happens is the results of the ALU is put back on the data bus and is stored back into the accumulator. That's why the word accumulator. You know, for example, you can write an instruction, you can add A plus B. It is an instruction add B. So you're adding the contents of two registers, A and B, and the result is put back into the A. So it's sort of accumulating, so it's put back in A. Again, if you execute A plus B, again it would, take the contents of A, add it to B, and again the results are put back in A. So this is a special register here. The contents of ALU are usually put back into the accumulator here, and this is an internal register temp. So if you, all right, so let's go forward and see. So the output of the ALU is put back here onto the data bus, and through that then transferred to the accumulator, or it can be transferred elsewhere. There is a flag register here. Flag register, which we will see later on. So what happens is when you do some logical operation and you end up getting a 0. Let's say you have some number coming in here and some number coming in here, and you do a logical AND operation. So when you do a logical AND operation, let's say you get a 0 here, right? And if you get a 0 here, what happens is it has a series of flags. So there is a 0 flag. It's like a flip-flop. So there's a 0 flag. So every time the content of the ALU goes 0, that flag is set. So it allows the user to know if the result is 0. And based on whether the result is 0 or not, you can take actions. You can branch to a different instruction and things like that. Okay, so the flag consists of series of flip-flops. It will indicate whether the result of ALU is 0 or not. Or whether, whenever you add something, note that if you're adding two 8-bit numbers, there's always a chance of carry outflow, right? The number is more than 8 bits, so there is a carry out. So it will indicate whenever there's a carry out, it will indicate that a carry out has occurred, right? And like that, there are other flags which we will come to. So that's a flag register here. These are the registers that we talked about. The internal B, C, D, E, H, L, stack pointer, program counter. All these registers are there inside my this thing, and they can all communicate as with the data bus. You have to load the registers with the data and all that here. All right, so there is an instruction register which we saw earlier in our small simple microprocessor. So when you fetch an instruction, it goes into a instruction register. So again, it comes via data bus, and there's usually a decoder, and there are other parts of the circuit which I'm not showing. So depending on the what comes in IR, specific sets of actions are taken. There's a timing and control. The inputs will show you later on. So these are signals that the microprocessor sends to the external world. External world, we'll see what these are. Timing and control signals here. Now, if you recall, I said that our 8085 microprocessor has 8-bit data bus. So this is 8-bit here. And the addresses are 16-bit. Now, because not enough pins are available, in the 8085 microprocessor. So what it does is the data bus, the pins that are associated with this data, it shares with the address. Okay, so you'll see in a minute what happens. So, for example, from the program counters contain 16-bit address for the memory here. So this is the red one is the address part here. So it isn't usually when you're driving external circuitry, you add buffers here, and so what happens is note that so we have 8 lines here and 8 lines here. So the address that comes in from here, 8 of them appear over here, and 8 of them appear over here. So these pins that are there, they serve both the purpose of carrying the address as well as carrying the data. So they are multiplexed. The lower 8 bits of the address and the data are multiplexed onto the same set of pins here. So how are they shared and all that we'll see here. Okay, so that's where, for example, the address appears here. These are the higher 8 bits and the lower 8 bits, and that's where the data will also appear. So the data will also appear here at this particular point here. And these are some of the signals that the microprocessor sends or to the external world. A microprocessor has to communicate with memory, has to communicate with other things that are there here. The external world can also sort of interrupt the microprocessor. Normally the microprocessor would be continuously fetching instruction, executing it. Right? But let's say if you want the microprocessor to do something specific, let's say some external device can, as the name indicates, can send an interrupt and cause the microprocessor to halt its current execution, and then depending on the interrupt, service that particular interrupt, do what that interrupt is asking it to do. So there is an interrupt control part here, and there is a serial input-output control here. You can receive the data. See, it's not just the microprocessor wants to communicate not just with the memory, but wants to communicate with other things also. I may have a keyboard, I may have a mouse or whatever, a lot of things connected to my microprocessor, right? So this allows a serial communication. Serial means 1-bit communication. So you can receive 1 bit from the external world into your microprocessor, and the microprocessor can send 1-bit data out also. All right, so if there is an LED that is there and you want to, for whatever reason, you want to make the LED blink, right? So LED blink means you give 1, 0, 1, 0 in particular order, right? So you can send, microprocessor can send a data here at this particular point. This one can go to the LED circuit and make the LED blink on for a certain time or for a certain time, just as an example of that it can communicate with the external world through the serial input output. It can communicate with the external world through these 8-bit lines also. These 8-bit address and data bus, these can also go to the external world besides the memory, and you can communicate through that as well. All right, so that's the simplified view of what our 8085 microprocessor looks like. Okay, data bus, ALU, the internal registers that are there here, and some timing and control, and some buffers to for address and data bus, and an interrupt control, and the serial input output. Okay, these are the major blocks that you see of your 8085 microprocessor. All right, as I said, I was showing you this particular picture here last time. So this is the internal conceptual block diagram, and this is how they are actually distributed here. In this particular one, you can see, we have large number of instructions. More than 200 instructions, which means that if you think about it, the instructions come in IR, there's a decoding circuit, and all those control signals have to be generated. Control signals for all of these that you see here, all of these here, all of these here, and timing and control. So the control unit is fairly complex. Control unit is fairly complex, occupies a fairly large area, right? And you can see why, for example, if I don't have the exact area of this particular one, but you can see all the pins are distributed. All the pins are distributed all along. And so if you use a separate memory and a separate data bus, so separate memory would have required 16 pins and 8 pins would have gone to data. So 16 and 8, 24 pins would have gone just there. And so the remaining pins, if you have a 40-pin package, so you have very few pins remaining for the rest of the tasks that are there. So it's for that reason that the address and the data bus have been multiplexed. but there are consequences, of course, of that. Okay. All right. So in terms of the pins, what are there? So it's a 40 pin. So this was the architecture that we drew. So let's quickly go over the pins. Note that these are the address, and when we call it AD, it means that these pins serve both as address as well as data. AD0 to AD7. So these are address as well as data pins. On the other hand, these are pure address pins. These are the upper byte of upper bits of address, and these will carry the lower bits of address. Okay, so these are the address and the data here. These are all the external signals that I was talking about here, timing and control that you see here. So the microprocessor, for example, when a microprocessor wants to read from the memory, it has to indicate to the memory that I'm reading it. So it will give a signal on the read here. And read bar means it's active when it is low. So the microprocessor will indicate a 0 on this particular one, and the memory then gets a signal to place the data onto the bus here. So like that, there's a read bar, there's a write bar, and we'll see all of that, okay? There's, of course, a reset pin. You can reset the microprocessor. The microprocessor then goes back to the program counter will be stored with 0000, goes back to the first place in the memory here. Registers may be initialized, so all of that. And when you give a reset in, the microprocessor also produces a reset out, because there are other systems connected to 8085. So when you're resetting your microprocessor, you may want to reset other systems as well. Okay, so it allows a reset pin out also. So these are all the control signals that are available here. These are the SOD and SID are for serial communication. As I said, serial data communication here. Serial input and serial output. So these are for that. This we will see. These are for communication with the memory. Separate communication with the memory we'll see later on. These are all the pins that are available for reset, for interrupts. So you can interrupt a microprocessor through various means, RST 7.5, 6.5, and all of that here. So there are various interrupts that are there here. You can connect different devices here. So a device may be connected to 5.5, and whenever it wants to, it wants attention, it can put a interrupt on this particular pin. And then the microprocessor will monitor this, and then accordingly, whatever action needs to be taken can then be taken. So it's sort of interrupt here. And these are the pins for connecting, the whole thing is a clock system. And many of these microprocessors, the clock that you see here, so these are pins X1 and X2. And the clock is generated through a piezoelectric quartz crystal. It's in these early microprocessors, even now. So this is a piezoelectric quartz crystal here, and and the rest of the circuitry is all inside. And for example, there are quartz crystals of different frequencies. For example, I could use a 6 megahertz quartz crystal, and 6 megahertz quartz crystal I can connect between X1 and X2, and I can connect a capacitor. The manufacturer tells what value of capacitance and all that to take. And then what will happen is the inside circuitry will generate a clock. And the clock would be half the frequency of the crystal that you connect here, the quartz crystal that you connect here. So if you connect a crystal of 6 megahertz, the internal clock frequency would be half of that, which is 3 megahertz. So that's for generating the clock. And the microprocessor, the microprocessor also has a pin so that the clock can be given to other systems as well. For synchronization and all that, the clock is available to any external system which wants to use it here. A little bit about this quartz crystal, for example. What is so interesting about quartz crystal? So you can buy these. They come in, depending on the size and the geometry, you get 3 megahertz, 6 megahertz, different kinds of quartz crystal, 20 megahertz here. So when you look at quartz, it can be modeled in terms of this here, in terms of a equivalent circuit that you see here, R, L, C, and C naught here. Right, so the quartz crystal can be modeled in this form. And what is very interesting is when I look at this particular one, note that this RLC will go through a series resonance here, right? Series resonance here. And beyond the series resonance, if you go at a frequency higher than the series resonance will come when the reactance of this cancels this. So when I go to a frequency higher than when series resonance occurs, then the inductance dominates over the capacitance. So I get a behavior, this part acts as inductive. And this inductive part, then you have C here, so you get parallel resonance here, right, at a certain frequency. So what is interesting about a quartz is that there's a very, very narrow range of frequency where this whole quartz crystal behaves as inductive, acts as an inductor. So with this inductor and an external capacitor, then you can make a tuned circuit and then you can make an oscillator. And because the frequencies, where it acts as an inductor is so very narrow, so you get a very, very precise frequency of oscillation. Okay, so that's why it's a naturally occurring substance, piezoelectric substance here. And if you use it in an oscillator, you get very, very sharp oscillation frequency, because it acts as an inductor over a very, very narrow range here. And so you can see here frequency tolerance in parts per million here, and very good temperature stability also. So highly temperature stable as compared to if you simply use an inductor or a capacitor, those are not very stable quantities. The values may drift. While here, these are very, very sharply defined. So in a sense, what you find is a very high Q system here, very, very high Q. When the frequency ranges are very narrow, then it's a very, very high Q system here. Okay, so that's why quartz crystals are commonly used in oscillators to build very, very stable oscillators here. Okay, so that's what is being employed here. A very stable, let's say a 6 megahertz quartz crystal, and then you end up getting an internal very stable clock of 3 megahertz. All right, so this range is very, very narrow here. Okay, before we proceed, just a reminder to all of you about whenever we talk about these microprocessors, if I have a 16-bit address bus and all that, so I'm not going to write 10000, it becomes intractable and all that. So what we do is the common notation is a hex notation, hexadecimal. So all of you know what you do is you take 4 bits at a time. So hex is here up to 9, and then 1010 becomes A, B, C, D, E, F, and then so you take 4 bits at a time and convert them into a hex notation here. So 1011 becomes a B. So it's still binary, but it's a hexadecimal notation here. A, 0, and 4. So instead of writing this binary pattern here, we'll simply write 40AB. So that's a convenient way of writing the address and even the data. If the data is a 8-bit data here, we'll simply write AB, right? Instead of writing 1010 and all that. Okay. Okay. So what are the instructions in my microprocessor? So keep in mind, these are the registers that are there here. So the instructions that are there in a microprocessor generally would consist of 2 parts here. They will consist of an opcode. One part is opcode, and the other part is operand. Opcode means it tells you what that instruction is supposed to do. It could be an add. So the opcode could be add. And operand is it has to do addition on something, some data. So this operand carries that information on. That addition operation has to be done on some data. So the operand carries that particular information, or what that thing is on which you want to do addition operation. So in general, it would be opcode plus some operand. It may be that there is no operand. You may be wondering, if there's no operand, then this opcode, what is it doing? Well, in the instruction itself, it is implied on what you're doing the addition. Okay, the instruction itself, implies where on which set of registers and all that the addition operation has to be done here. So this is in general. So all opcodes are 8 bits. 8 bits here. So these decide the instructions. Which instruction am I doing here? The instructions can be broadly classified into the following categories. Data transfer. Okay. Example of data transfer is, we'll see these in a minute. So for example, there can be an instruction which is MVIB. So this is written in mnemonics, MVIB 07H. Okay. So there's an instruction like this here. What does the first one denote? The first one, so in the memory actually, in the actual memory, it would be stored like this here. 06, and then in the next place in the memory, it would be stored 07. So the memory has a 06 stored in it and a 07 stored in it. And that's the complete instruction. Now, when the microprocessor fetches, it will fetch 06 first. And what is the 06? 06 is the first part here, the opcode. And what does it, microprocessor will interpret? It says MVIB. move immediate into the register B. Move immediate into the register B. What does immediate mean? Well, in the next byte is the data, actual data which is stored here. So take this data and put it in register B. So this is what is happening. 07 is loaded in register B. Okay, so the complete instruction is 0607. H denotes that it's a hex notation. Okay, so that's what is stored in our microprocessor here. MVIB 07. And that copies the data 07 into your microprocessor, into the register B. Another could be a instruction which has 3 bytes, right? One opcode. The first one is always the opcode. 3AH is the opcode. Operand in this case is 16 bits. So LDA 4400H. So 3A0044. So this is what will be stored in the memory. 3A first, then 00, and then 44. So what the microprocessor will do, will show you how it will execute that instruction. So 3A denotes that it's an LDA instruction. What does it mean? You're loading accumulator. And what are you loading into accumulator? Well, 4400 is an address of the memory where the data is located. So my data that I want to load in accumulator is located at memory location 4400. In this case, the data was given in the instruction itself. While in this case, one is saying, well, my data is located at some memory location 4400. And whatever data is located in that, that's why the brackets, whatever data is located in that memory location has to be then transferred to A. So it's a 3 byte long instruction here. First one is always an opcode, which tells a microprocessor what to do. What is that operation all about? This is load in accumulator. This is move into register B, data which lies in the next memory location. Okay, so there are these data transfer operations here. Then there are, we'll look into these. So there are arithmetic and logic operations, which we understand. For example, there can be an instruction which is simply add B. Add B. So this is, note that it's a 1 byte instruction. That's what I was talking about. There's only an opcode. There is no data, there's no operand as such after that. It's a single byte instruction which is called add B. Now when add B comes, it's understood that what is happening is you're taking the contents of B, you're taking the content of A, adding them up and putting back into A. So the microprocessor, once it gets this instruction 80, will understand that there is no data which is lying in some memory location or somewhere else. Whatever I need to do is all there in A and B, so I need to do this operation. So it's a single byte instruction there. And like that, there would be many instructions, add, subtract, logical AND, and all of that here. There are branch instructions. So when you're normally going through your code one instruction after another, you may want to branch to some other location. So for example, this will say jump, J refers to jump, and Z means it's referring to the flag. It says if the flag is 0. Remember we said flags are there. When you do some operations, the flags are set. There's a 0 flag, carry flag, and things like that. So it says if jump 0. So what it says is, look at the contents of the accumulator. Look at the contents of the accumulator here. If the contents of the accumulator is 0, then what happens is the flag is set. So it says if the flag is set, then jump to this site, this memory address, which means now the program will jump to that 4400H and will start executing from there. Okay, so these are branch instructions here. Normally what happens is the program will go, let's say from 3300, 3301, 33, it goes sequentially. But then once it encounters a instruction like this, then it will jump to that particular memory location and start executing the code from there. Okay, a jump instruction. Then there are control. There are things to be controlled, for example, interrupts and all of that. So there are control instructions here. Okay, so 4 broad classes of instructions are there. Data transfer, arithmetic and logic, branch, and then control. For example, enable interrupts, disable interrupts, and there are other things as well, which are there, which have the control aspects that are there. So these are the 4 classes of instructions that you see here. All right. So normally when one is programming the microprocessor, when I write a code, so when I write a code like this, LDA4400H, what does it say? Load into the accumulator the contents of this memory location, MVIB07. So it says what? Load the data 07 into register B, add B. So what have I done through this 3 lines? Whatever is in the memory location, here I've loaded it in A. In B, I've loaded 07. I've added them together. And where is the result available? In A itself. So thereby, I've added 2 numbers. And the result is available in A. So when I write, in mnemonics like this, what we generally call is an assembly language program. But remember, the microprocessor will understand only 0010s and all that, right? So I need an assembler. So I can write it in a language like this, load A, MVIB and all that, I can write a program. But I need an assembler which will convert this into, each one of those mnemonics, it will convert it into the proper bits corresponding to those instructions here. So LDA, for example, is 3A. So what will actually be stored in the memory is 3A, then the lower bytes here, 00, 00, then 44. So that's the first instruction that you see here. MVIB07, the code for MVIB is 06, and then you load the data 07. And then the code for 8B is ATH. So I need a assembler, a program which will take this and translate it into this. Well, if you want, you can directly program the microprocessor in this also, but that's not very convenient, right? And directly adding this is what we call as the machine code. This is a machine code. This is the code that the machine understands, these binary patterns that are there. Well, this is more convenient for us to write it. So this is what is called assembly language programming of the microprocessor. Even this is not very convenient. So typically, you would want to write a C code, and then you would want a compiler. So you write everything in a C code, and then you have a compiler which knows the instruction sets of a microprocessor here. So the compiler will translate into finally the machine code. So normally, when you are programming the microprocessor, what you're doing is you're writing a C code and you have a compiler available. So it will translate, do everything, and will generate the machine code for you. Okay. Now, of course, the quality of the compiler becomes very important. A good compiler will take your code and very efficiently translate it into the set of instructions that the microprocessor can execute. The quality of the compiler is very important. Okay. You can have many vendors giving you compilers, right? One compiler may be better than the other. Because how you map a code into these low-lying instructions can be done in many different ways. Okay, you have many different ways of doing it. Some may be more efficient, some may take less time, some may take more time here and all that. So when you write a C code, you don't know what is really going on. If you write in assembly language, you are closer to the microprocessor. You know which register to put in and where to read and all that. So you get a better feel for, if you're trying to understand a microprocessor, how it executes instructions and all that, this is the place to work, assembly language. This is too difficult. Actually going ahead and putting the machine codes and all that, remembering all that is too difficult, right? So this is the place, if you want to understand a microprocessor, take a microprocessor and do an assembly language coding of different programs or different things that you want to accomplish. So assembly language coding is a place where you get a feel for the microprocessor. All right, so let's see. Now note that your microprocessor, one of the basic things of a microprocessor is it has to fetch from the memory. It has to fetch things from the memory. It has to write back to the memory here. So how does it read from the memory? Our 8085 microprocessor here. Okay. So in a microprocessor, of course, everything is clock driven. So there is a clock running through our system here. Clock running through a system. And each clock cycle in 8085 terminology, each clock cycle is referred to what is called a T state. Okay, T1. There's a clock cycle 1, so it's called T1. T1 state here. This clock cycle 2, so it's called T2 state, and clock cycle 3 and T3 state. So I'm going to do here, illustrate memory read operation. So there is a memory somewhere here, which is connected to my microprocessor. Connected in what sense? Connected to the address bus, the data bus, and some of the control signals are also going to the memory. So memory is connected here. So what do I do? Well, the first thing that we do is the following. The microprocessor wants to read, so microprocessor will place an address on the address bus here. So now address bus is here, right? This is the red one is the address bus here. So A15 to A8, these are the upper byte of the address here. And the microprocessor will also place the address on this one here, on the data bus, which is actually because data bus and the lower address bits are multiplex. So microprocessor also places the address bus here in the T1 status. It places both the addresses here. Where will this address come from? Well, for example, if the microprocessor is fetching an instruction, if it's fetching an instruction, the first opcode, where is stored here? Is stored in the program counter. Program counter stores the address where the program is there, right? So what it will do is it will take the contents of the program counter here and place it into this and this here. Upper byte here, lower byte here from the program counter. Okay, so this is here. But now after putting it here, the address here and here, it can't keep the address here forever because on the same set of pins, I want to receive the data from the memory. So what the microprocessor does is it generates a control signal called ALE, address latch enable. It generates a signal. One of these signals is ALE signal here, address latch enable. So what it is telling, so externally, I must have somewhere a latch, a 8-bit latch. And what it will do is when I get a address latch enable, when it goes from high to low, this lower 8 bits of data will be latched into that particular one. So the lower 8 bits of the data is latched externally into a memory, a 8-bit memory, 8-bit latch. And this signal tells us that address latch enable. So now it frees up my data bus. Data bus no longer has to carry address because this part of the address has been latched into a external latch. Okay, so address latch enable. So now this is freed up. Now what happens is, so that's where, imagine that there's a latch here and this is coming here and there is an address latch enable and so this is latched here. So now I have upper 8 bits of data and lower 8 bits of data. All are available and they can go to the memory, right? And the data bus has been freed up. Data bus now can carry the data. It has been freed up and so this is there. And the microprocessor also generates all these control signals here. For example, there's a control signal called IO/memory bar. So when this is low, it indicates 0. It indicates that I'm doing a memory. I'm interacting with the memory. Or when this is 1, it says I'm not interacting with the memory, but with some other input-output device. S0 and S1, these are all indicative of that I'm performing a reading operation. Okay, so the microprocessor has to indicate these things. So these are control signals that are generated here. Then what it does is, after it has placed both the addresses, and then it gives a read signal, which goes low. One of the signals here is read, it goes low. So that when it goes low, that read signal goes to the memory and tells the memory to now place the data on the data bus. So after some time, the memory will place the data on the data bus here. Okay, these are not very precisely drawn. Okay, so don't. So effectively, what happens is, note that read signal goes low here, and the data becomes available in the T3 state. Data is available here in this particular state. So data is available on the address bus, and it's over here. All this bus here, so it's available here. Okay, so that's how now the data is available on the data bus. So it has read a data from the memory by putting a read signal low, and then the data becomes available in this T3 state here. And the data can be lashed into any of these registers here. You can transfer the data into, if you're reading an instruction, then you will transfer the data into IR. So in this part, you will enable IR, so the data goes into IR also. So it gets available here, and then eventually it gets lashed into IR also. So it goes into instruction register. If you are reading a data which has to go into accumulator, you will enable the accumulator here. So the data goes directly into the accumulator. So once it's available on the data bus, it can be routed wherever, depending on the instruction, it can be routed wherever you want here. ACC or instruction register or one of, other things that are there. So that's how the microprocessor is performing the read operation. How many clock cycles does it need? 3. 3 clock cycles to read the data from the memory here. Each clock cycle is what? If we are running a 3 megahertz clock, then it's 0.3 microsecond. Right? 3 megahertz is what? 0.3 microsecond, right? 0.3 micro, 1 over 3. 0.3 microsecond. So you can see 3, so it's taking roughly a microsecond to transfer a data from the memory into the microprocessor. 1 microsecond to transfer. This is an old microprocessor, okay? So 1 microsecond may appear to be not a very short duration. Write operation is also very similar. Except for reading, what you will need to do is look at that write operation. So again, these are the same things, placing an address here, placing both the lower and the upper bytes of the address here. Then address latch enable will latch it here. Then in T2 state, I will place the data. The microprocessor will place the data here on the address bus. Okay, so the data is placed by the microprocessor, and control signals again, talk about it. Write signal goes low, and then tells the microprocessor, tells the memory to latch the data into the memory location. Okay. So by the end of third state here, T3 state here, the data has been written into the memory. All right. Let's look at the execution of instruction MVIB07. All right, located at C050. So memory is what? 16-bit memory, right? 16-bit memory is there. And let's say there is a instruction MVIB07 located at that particular one. How will that instruction be actually located? MVIB is 06 and the data is 07. So this is the instruction which is located at this memory location. How will my microprocessor execute that particular instruction? So what will it do first? First thing it does is fetching the opcode. It has to fetch the opcode. Okay. So this is where the opcode fetching is taking place here. Memory read, right? We just talked about a memory read operation here. So note that upper bytes are C0 is placed here. Lower bytes is 50, so it will place 50 here. Where does this data come from? Program counter. Program counter has this data here, C050. Program counter keeps track of, where the different instructions are loaded here. So basically the contents of program counter are placed here in these. And, ALE, read and all that. So at the end of T3, what has it done? What has the microprocessor done at the end of these 3 states? 06 has been loaded. 06 has been read from the memory, and where will it go? Because remember, it is the opcode fetch part. So where will it transfer? Into the instruction register. It will transfer that 06 that it has been read here into the instruction register here. So in this T4 state here, this 06 has been transferred into the instruction register. It is decoded, and the microprocessor decides what to do next, what action to take next here. So this whole thing that you see here is what we call as the opcode fetch cycle. In these 4 clock states here, the opcode is fetched, decoded, and whatever is the next set of action decided, it all takes place in these 4. Okay, this is where the whole thing is decided. Now, what does the microprocessor? So 06 has gone into my instruction register. What does the microprocessor have to do now? What does this 06? What will it tell microprocessor? To read again. To read again what? From the memory, this data 07 and store it where? In register B. So what does it have to perform? Again a read cycle. A read cycle here. So this is what it performs, a read cycle. Now, a read cycle here, where is this located? 07 will be located as C051. So it's C0 and 51. Program counter has been incremented, right? So whenever you fetch a byte, then program counter will become C051. So it loads C051. And it is doing a memory read operation. So what will come from the memory? 07. And where will this go, 07? At the end of it, it will be latched in register B. So thereby, the microprocessor has executed the instruction MVIB07 located at C050 at this particular place here. How many clock cycles did it take? See, 4 clock cycles are always needed to fetch an opcode. 4 clock cycles, 3 to read a memory, to read the opcode, and 1 to decode the opcode. Decide what to do with it. So 4 clock cycles are needed to fetch the opcode and decide what to do. Okay, and the remaining 3 are, now in this case we only have to read, so it's again a memory read operation. Okay, so this is the together, this is what we call as in 8085 terminology, this whole thing is called machine 1, machine cycles. So in this is called the first machine cycle here, where the opcode is being fetched. This is called the next machine cycle, the second machine cycle where the data is being fetched. So the instructions are executed in 1 machine cycle, 2 machine cycles, or 3 machine cycles. Okay, it's like that. And each machine cycle has within it, you can see here, several clock states here. 4 clock states here. This is a simple memory read operation. That's also 3 clock states. Okay, so these are called machine cycles here. In the sense, these are a particular logical, particular step is being performed here, which is getting the opcode and deciding what to do. So that's 1 machine cycle number 1. Then fetching the data into the memory. That's machine cycle 2. All right. Execution of single byte instruction add B. What will the microprocessor do in this case? It's a single byte instruction. So what does it have to do? Fetch the instruction and decode it also. So everything is done in 1 machine cycle. 3 for fetching the opcode, ATH, and in this case it decides what needs to be done, and since no data, nothing else is required, it executes here itself in this T4 state. So in 4 clock cycles, the entire operation has been done. Add B operation. There are more complicated ones. Well, let's see. LDA4400H. Now, you want to tell how many machine cycles will it require? What all does it have to do? First is very clear. So I have this LDA4400H located at some memory location. So first machine cycle is what? Fetching the opcode, decoding it, and deciding what to do. So that I've already written. Okay, machine cycle 1. What has to happen next? What does 4400 mean? That at this address, a data is located. And you have to bring that data where? Into the accumulator. So what does it have to do next? Already the opcode has been fetched and we know now it's a LDA instruction. So what do I need to do next? Read the data, right? Read this memory location. Read what is that memory location here? M2. So I'm doing a reading operation. When I'm doing a reading operation, what do I get? 00. Then you will read again to read 44. So this again, 44H and 00 are all placed here. And then the data is brought into the accumulator here. So I have to execute 1, 2, 3, 4 machine cycles to execute this particular instruction here. And total number of clock cycles are 13 clock cycles. That's how it's able to execute this.
What do S0 S1 do?
Huh?
What do S0?
S0 and S1 are indicating what is happening. What is my microprocessor doing? 1, 0, 0, 0. So am I doing a read operation, memory read? Am I doing a memory write? Am I doing a input output, some other input output read or write? So it's indicating. Because there are many other things, memory is connected and many other devices may be connected to the microprocessor. So they get to know what is really happening. Okay, so this is a LDA4400H. That's how the microprocessor executes the entire instruction. Alright, so let's stop here. We'll go through the some more things about this particular microprocessor.